Hello, today is the last section of chapter 2 of polynomial functions. We're going to be approximating the zeros of a function. Sometimes a function does not have any rational roots, so therefore we have to approximate the real roots that we do have. So I have a function f of x here that we're going to try to find all the roots of. We're going to go through the process of finding. First thing I'd probably look at is to see if I could factor this possibly. And you could factor out an x squared by grouping here and do x plus 2. But you can see pretty quickly that your two binomials are not going to be the same. So it's probably what I'd look at first. Knowing that it can't be factored, then I'd look at the rational root theorem and try to figure out what are some possible rational roots of this polynomial function. So we have the factors of 5 over the factors of q, which is just 1. So the only possible rational roots we have are plus or minus 1 and 5. So we could take a look at that on the graphing calculator. We could also just plug them in and see if we get a remainder of 0. So we could plug in f of negative 1. We could plug in f of 1, f of negative 5, and f of 5. And what we'll find out is actually that none of these are equal to 0. And so it appears that there's no rational roots. So let's look at the graphing calculator real quick just to kind of see what it is that we're looking at. And you see that the graph, in terms of its degree, it has three roots. So when we look at the graphing calculator, we actually see all of them. Here, here, and here. But what we look at is we realize they don't cross at any of those points that we just said, 1 and 5. You got 1 is right here. 5 over here, negative 1 and negative 5, and it doesn't cross at any of those 4 points, but it does cross twice on the negative side and once on the positive side. So, what are the solutions? How do we find that out? Well, they're not rational, so what do we do next? Well, maybe what I would look at is, let's do Descartes' rule of sign and see what more information we can get from that. So, we will practice Descartes' rule of sign, and let's look at f of x. Sign changes. We got a positive, a negative, and a negative. So it looks like we only have one sign change. So we have one sign change, and then if we do f of negative x, we'll have a negative when you plug it in. Plug in negative to x squared and get positive. Plug in negative to x and get negative 3 times negative x, which would be positive. And then the last one is negative. So in this one we have 1, 2 sign changes. So with the negative we have 2 or 0, and the positive we only have 1. So what are the different combinations? Well, we could have 1, 2, or we could have 1, 0. That's it, with a total of 3. That gives me 0 imaginary for the first one and 2 imaginary for the second one. But we know there's no imaginary because from the graph it shows all 3 of them, and you can see that 2 of them are negative here and here, and that one of them is positive. So we actually know from Descartes' rule of sign that this is what we're looking at, and that we verify that on the graphing calculator. So what's kind of our next step here? What is it that we're supposed to do? We know the roots exist. We can see that on the calculator, but we don't know what they are, and they're not rational, so they've got to be irrational. So what we kind of have here is, if I can maybe move that up a little bit, Descartes' rule of sign indicates that there are real roots. Because there are no rational roots, we need to approximate the real roots that we have. And so what's that kind of next step? Well, the next thing that we get into is we're going to get into this intermediate value theorem. And it might seem obvious as we go through it, but it's very important for what we're going to be doing here. Alright, so the intermediate value theorem, if a and b are real numbers such that a must be less than b, and f of x is a polynomial function where the output of f of a and f of b there is not equal, then in the interval between a and b, f of x takes on every value between f of a and f of b. A lot of words, a lot of information. Let's get a picture. So a has to be less than b. So I'll put a, b. call this f of a. So we got a point here, and we'll call this f of b. So whatever this polynomial function might look like, what the intermediate value theorem is saying is that the interval between a and b, so that's from here to here, takes on every value from f of a to f of b. And so to change colors here just to show you, it's talking about all values from here to here. It's taking on every value in between that. There's no breaks in the graph. So once again, maybe seems obvious, but very important for what we're going to do. Because of this, we can conclude that if f of x is a polynomial function with real coefficients, and a and b are real numbers, where f of a is less than 0 this time, and f of b is greater than 0, the function has at least one real root between a and b. Why is that? Well, let's take a look. So we'll do the same thing, but on this one I'm going to make sure that the f of a is less than 0. So we can put a and b, but now f of b is still there, but I'm going to move f of a so that it's less than 0 and f of b is greater than 0. So I'll plot my 2 points, and what it's saying is, alright, that if this is true, then you will at least have one real root between a and b. It's got to cross the x-axis if f of a is less than 0 and f of b is greater than 0. At some point it has to cross. So kind of put the intermediate value theorem in with what we just talked about, and it's saying it takes on every value, so there's no way it's going to skip over the x-axis. So kind of a lot of information there, but it's very important in terms of what we're going to be solving for. So we're going to talk about something called the upper and lower bound rule. So once again, kind of a lot of information here, and then we'll kind of go through and look at an example. A real number b is an upper bound for real roots of a function if no zeros are greater than b. So once again, this value is an upper bound for real roots, alright, as long as there's no zeros greater than that value. And it is a lower bound if there are no real zeros less than b. Alright, so how do we find that upper and lower bound? We're basically trying to figure out what section of the graph we can focus on as to where it's crossing the x-axis. So once again, just some information up front. Let f of x be a polynomial function with real coefficients and a positive leading coefficient. So we have to have that positive leading coefficient. And what we're going to do is we're going to divide by x minus whatever that c value is that we use using synthetic division. So we're going to pick a value that is greater than 0 for the upper bound, and then we'll pick a value less than 0 for the lower bound. So we just start with 1, and then we'll go up to 2, 3, 4, and same thing with the lower bound, -1, -2, and so on. And so for the upper bound, what we're looking for is each number in the last row, which is your quotient, is either positive or 0. So as long as it's positive or 0, then we know C is an upper bound. When it's less than 0, alright, -1, -2, then once again for the quotient we're looking for alternating positive and negative, and 0 counts for positive or negative. And if that's the case, then we have found a lower bound. Alright, so let's take a look at an example to kind of get a better idea as to what we're trying to find here. Find the upper and lower bounds for the function. So let's take a look at this, and we're going to pick the upper bound first. We're going to pick a value that is greater than 0. So I would just start with 1, do synthetic division, make sure if there's any missing terms you plug that in, carry the 1 down, 1 times 1 is 1, and then I get -4, and I can stop, because if you go back to the last slide, for the upper bound we're looking for either positive or 0. Well, what we just found was we found a -4. Okay, well that's not going to be an upper bound. So we could pick 2 next, but what you might find out when you go to pick 2 is you're running the same problem. You got 1 times 2 now instead of 1 times 1, and now you get negative 3. So it still didn't change. So what would be that next value that you actually would plug in here so that you get a 0 or a positive? And that answer would be 5. So we can actually jump to 5 because we know 5 times 1 is 5. That's going to give us a 0. No number before that's going to work. And now we can continue to see if this works. 5 times 0 is 0. 3 plus 0 is 3. And then 5 times 3 is 15, and you get 17. So it looks like we have all positives or 0 there. So we found the upper bound to be x equals 5. So the upper bound is at x equals 5. And so there, the function will not cross after x equals 5. That's that upper bound. So we know we won't have any solutions greater than 5. And then we'll do the same thing with the lower bound. We'll pick values of c that are less than 0. Once again, I would just start with negative 1. And this one, just to go back to make sure, this one we're looking for alternating positive and negative. So the first one is positive because the leading coefficient has to be positive. 1 times negative 1 is negative 1. Add those up, you get negative 6. So far, so good. Negative 1 times 6 is positive 6. Add them up, you get 9. Positive, negative, positive. So far, so good. Negative 1 times 9 is negative 9. You get negative 7. So positive, negative, positive, negative. That's alternating signs, which is what you need. So we actually found the lower bound to be x equals negative 1. So the upper and lower bound of this graph is saying that whatever's going on in this polynomial function from negative 1 to 5, the graph is crossing somewhere between here. There's no way it's crossing anywhere else on the x-axis besides between negative 1 and 5. And so you could graph that on your calculator to verify that. But that's what the upper and lower bound state. So what I want to do is go back to the original question. All right, find the roots of the polynomial function. This is the one we started with. We know it crosses. How are we going to find that information? All right, so let's go ahead and find the upper and lower bound for this one to kind of practice that idea again. So upper bound, we're going to choose c greater than 0. And so we'll start with 1 again. 1, 2, negative 3, negative 5. Carry down the 1. And that's okay so far. 1 times 0 is negative 5. So we ran into a problem at the very end. So let's not jump to any conclusions and think it's going to go higher than 2. Let's just put 2 in and see what happens. And do it again. Carry down the 1. 1 times 2 is 2. Now you're at 4, 8. So the numbers are getting a little bit larger. And then 2 times 5 is 10 with 5 at the end. So it looks like we found the upper bound for this problem to be at x equals 2. And then let's go and do the lower bound. So when c is less than 0, once again we'll start with negative 1 and just see where that gets us. Carry down the 1. And so right away that second one is a positive. We need it to be a negative. So let's go to negative 2. Carry down the 1. 0 is fine. Negative 2 times 0 is 0. And then we add negative 3. We're supposed to get positive, negative, positive. So we get a negative here, so that's not going to work. So we need to go to negative 3. 1, 2, negative 3, negative 5. Carry down the 1. 1 times negative 3 is negative 3. Negative 1, positive, negative. Then we get a positive 3, so we get 0 here. So positive, negative, positive. So far everything's good. And then we get positive, negative, positive, negative. 0 counts as positive or negative, so that looks like it works. So we found that our lower bound is at x equals negative 3. So we know that everything on our graph is going to be between -3 and 2. That's where all those main points fall. And so we can go back to the graph and you can see nothing is below the -3 and nothing is above the 2. And that's what we found out with the upper and lower bounds. But let's take this a step further. We know where the graph is going to cross because these values right here, these are your remainders. These are your outputs. Okay? And so what I want to do, zoom out a little bit here, is if I say, alright, what's f of, let's go to -3, f of -2, f of -1, f of 0, f of 1, and f of 2. And what is the output on these functions, and why is that important? Well, let's take a look. F of -3 was at -5. F at -2 we never finished, so let me finish it real quick. -2 times -3 would have been 6, so the output was 1. Same thing on f of -1, I'll finish that one. That was also at that one's at -1. F of 0, if you plug that one in, you can just plug that into the function and get 0 plus 0 minus 5 to get -5. And then plug in f of 1, that was also at -5, and then f of 2 was at 5. Well, we don't need synthetic division to do that. We can just plug those numbers into the function and get what the output is or what the remainder is. So what do these values mean? What is going on here, and why is this important? Well, what you're looking at is the output values. Well, what happens between -1 and 5? So at -3, we're at -5, somewhere down here. And then at -2, we're at +1. Well, what has to happen between these 2 points? It has to cross the x-axis. So now, we know that between these two, we have a solution, we have a 0. So when it changes from positive to negative, which it does again here, it's going to cross the x-axis. Now from -1 to 0 it stays negative, from 0 to 1 it stays negative, but then from 1 to 2 it crosses again. And so that's where our 3 zeros are located. They're in between x equals -3 and -2, x equals -2 and -1, and between x equals 1 and 2. And so the last thing that I want to do here is I want to take this and I want you guys to approximate it to the nearest tenth. So right now we know that our zeros are between x equals -3 and x equals -2. We also know that they're between x equals -2 and x equals -1. And then we also know at x equals 1 and x equals 2, there's a 0. Let's pick one of these and find what it is to the nearest tenth. So we can we'll do the positive, x equals 1 and x equals 2. And we're just going to pick values between 1 and 2, but, whoops, that wasn't right anyway, so don't ignore that. So we're going to pick values in between 1 and 2, but 1 and 2, you know, if you look, the output was between -5 and 5, so somewhere close to the middle of 1 and 2, so I wouldn't start with 1.1, but maybe start with 1.4, 1.5, 1.6, something like that. So we'll try to find f of let's do 1.4, 1.5, 1.6, and let's just do 1.7 and see where we get. So what are these output values? You guys can use your graphing calculator to figure these values out. on mine here, I don't know with this calculator if I can go to, let's see if I can go to table. Oh wow. And go to table set. I want to start my table at 1 point, what did I say, 4? And then I can go up by 0.1 each time. So let's see if this works. Oh, there was an error. So at 1.1, you can see where you're looking for, where is it going to go from positive to negative or negative to positive. So you can see as we get closer to 1.5, that's negative 1.625. And then at 1.6, it's negative 0.584, so it's still below the x-axis. And then at 1.7, it jumps above at 0.593. So I'm going to write those two numbers down, 1.6 and 1.7. So at 1.6, we had negative 0.584, I believe. I'll go back and look. And then at 1.7, 0.593. Let me go back real quick. 584 and 593. Okay? And so right here, we know that there's that 0 because it changes from the x-axis. It changes the output from negative to positive, so it crosses the x-axis somewhere between 1.6 and 1.7. Now if I want you to round to the nearest tenth, which one are you going to use, 1.6 or 1.7? Well, which one of these values is closer to the x-axis? Negative 0.584 or 0.593? Well, the 0.584 is closer, so we would approximate this as x is approximately 1.6. That's one of the 3 zeros that you would be finding. Okay, and then we would do the same thing between negative 3 and negative 2, and negative 2 and negative 1. And don't hesitate to use the calculator. Just go to your table set, which is above the table, and then change where you're going to start. So I would start at, what was the one? Negative 2 and negative 3. So if I start at negative 3, and I go to 0.1 again, and then I go to my table, then I can look from negative 3, it was at negative 5, which we knew that, and you're at negative, 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 negative 2.4, you're still at negative, and then negative 2.3, you jump to 0.313. So from negative to positive, which one is closer to 0? The negative 0.104. So one of your answers would be negative 2.4 in terms of your solution. But you would have to show this work to justify your answer. So let me, just so you know, this is what I want to see before you answer the question. Just like this, I would want to see to show me that you know where the solutions are between negative 3, negative 2, negative 2, negative 1, and 1, 2. Okay? So that wraps up the last section, or the last day of notes that we have before a polynomial function test. There is a worksheet that goes with this, so you can get that off Schoology, or you can get it in class. So once again, our focus today was approximating the zeros of the function using Descartes' rule assigned rational root theorem. We talked to intermediate value theorem to understand that it's going to cross the x-axis. And then we did our upper and lower bounds. And to be able to find those, that just focuses more on where does it actually cross on the x-axis, so we can be a little bit more specific as to what we're trying to find out. Thanks.